Large language models face strict limits on context window size and knowledge cutoff dates. Retrieval Augmented Generation bypasses these constraints by fetching external data in real time from a specialized database before generating a response. Raw text cannot be compared mathematically. Embedding models transform sentences into long arrays of numbers, called vectors. These numerical representations capture the underlying meaning rather than just matching specific words or characters. Vectors reside in a high-dimensional coordinate system. In this mathematical space, related concepts are positioned physically close to each other. For example, the vector for kitten is located near the vector for cat, but far from the vector for skyscraper. Cosine similarity measures the angle between two vectors, rather than the absolute distance between their endpoints. This approach is highly effective because it focuses on the direction of the meaning, ignoring the total length or word count of the document. Euclidean distance, or L2 distance, measures the straight line between 2 points in space. Architects choose this metric when the magnitude of the embedding is significant, which often occurs in specialized image recognition or audio processing tasks. The dot product calculation is the fastest metric for hardware to compute. If vectors are normalized to a length of 1, the dot product results in the same ranking as cosine similarity, significantly reducing the computational overhead during massive search operations.
A flat search compares a query against every single record in the database. While perfectly accurate, the time required grows linearly with the database size. For millions of documents, this creates unacceptable latency for real-time applications. Approximate nearest neighbor algorithms trade a tiny fraction of accuracy for massive gains in speed. These methods use clever indexing structures to narrow down the search area, allowing the system to find relevant data in milliseconds, regardless of the database size. Hierarchical Navigable Small Worlds, or HNWS, is the most popular indexing method. It creates a multi-layered graph where the top layers contain only a few points for fast traversal, and the bottom layers contain all points for high precision. The search starts at the top layer, with large jumps between nodes to quickly reach the general neighborhood of the query. The algorithm then descends to lower layers, refining the search, until it identifies the exact nearest neighbors at the base level. The inverted file index method partitions the vector space into clusters using centroids. At search time, the system only explores the clusters whose centroids are closest to the query vector, effectively ignoring the vast majority of irrelevant data points. Product quantization reduces memory usage by splitting long vectors into smaller subvectors. Each subvector is then replaced by a short code from a predefined codebook, allowing billions of vectors to fit into available system memory. Effective retrieval depends on how documents are segmented. Small chunks capture specific details but lose context, while large chunks provide broad context but dilute specific facts. Architects must find the balance based on the typical query length and detail. Fixed-size chunking often splits a critical sentence in half, destroying its meaning. Using an overlap, such as 20% of the chunk size, ensures that semantic context is preserved across the boundaries of adjacent segments. Recursive splitting attempts to break text at logical points, like double new lines, then single new lines, and finally spaces. This hierarchy ensures that paragraphs and sentences stay together as much as possible, maintaining the logical structure for the embedding model. Semantic chunking monitors the distance between the embeddings of adjacent sentences. When the semantic meaning shifts significantly, the system triggers a new chunk. This ensures each segment contains a single coherent topic, regardless of its physical length. Vector search alone is blind to structured data. By attaching metadata like timestamps, document IDs, or categories to each vector, analysts can restrict searches to specific subsets, drastically improving both the relevance of results and the speed of execution. Pre-filtering applies constraints before the vector search, ensuring every result meets the metadata criteria. Post-filtering performs the search first and then removes invalid results, which can lead to returning fewer results than the requested top K value. Hybrid search combines dense vector retrieval with traditional sparse keyword search. While vectors excel at understanding intent, keyword search is superior for finding specific technical terms, product codes, or rare names that might be overlooked in the vector space. Best Matching 25 is the industry standard algorithm for sparse search. It ranks documents based on term frequency and inverse document frequency. Integrating this with vector scores creates a robust system that handles both conceptual queries and exact matches. Reciprocal rank fusion merges two different ranked lists without needing to normalize their scores. It calculates a new score based on the reciprocal of the rank in each list, effectively rewarding documents that appear near the top of both search methods. A single user query might be too brief for an effective search. Query expansion uses a large language model to generate multiple variations of the query, exploring different synonyms and perspectives to ensure the most relevant documents are pulled from the database. Hypothetical document embeddings, or HyDE, works by having an LLM generate a fake answer to the query first. The system then embeds this fake answer and uses it as the search vector, because a document is semantically closer to another document than to a short question. Biencoders produce vectors for fast initial retrieval, but they lose context between the query and document. A cross-encoder takes the top results and the query together to calculate a highly precise relevance score, discarding any low-quality matches.
Re-ranking adds significant latency because it requires a more complex model to process every retrieved candidate. Systems typically limit re-ranking to the top 20 or 50 documents to maintain a fast user experience while maximizing final answer quality. Large documents with diverse topics are best handled by generating multiple vectors per document. This allows a search for a specific detail in Section 4 to succeed even if the overall document summary is not a close semantic match to the query. Modern vector databases are multimodal. Using models like CLIP, developers can embed images and tables into the same vector space as text. This enables a user to search for a visual diagram using a natural language description. When building software for multiple clients, developers must isolate data. Partitions ensure that users only query their own vectors. This is achieved through physical hardware separation or virtual namespaces within a single database instance. Namespaces provide logical isolation within an index. Using namespaces prevent crosstalk between different versions of your knowledge base or different user groups, allowing for much easier maintenance and granular access control in enterprise environments. Updating a vector index is computationally expensive. There is always a trade-off between write throughput and read latency. High-speed indexing usually requires a background process to rebuild the graph, which may result in a delay before new data becomes searchable. For applications with thousands of updates per second, use a buffer or a write-ahead log. The database can then perform batch indexing, which is far more efficient than recalculating the hierarchical graph for every individual vector insertion. In-memory databases offer the lowest latency, but are limited by expensive RAM. Disk-based indices, like disk-ANN, use clever caching of frequently accessed nodes to provide near-memory speeds, while storing the vast majority of the vector data on cheaper SSD storage. As vectors are updated or deleted, the underlying graph becomes fragmented. Regular compaction processes remove tombstones and rebalance the links between nodes, preventing search performance from degrading over time as the dataset evolves. Large language models often ignore information located in the middle of a very long prompt. To counter this, keep your retrieved context concise and place the most critical information at the very beginning or the very end of the injected text. Precision measures how many retrieved documents are actually relevant. Recall measures how many of the total relevant documents were successfully found. A high-performance system must optimize for both to ensure the LLM has all the facts without being overwhelmed by noise. Recall at K is the standard metric for approximate search. It measures the probability that the true nearest neighbor is included within the top K results. Increasing K improves recall, but increases the cost and latency of the subsequent generation step.
The RAGAS framework uses a large language model to evaluate the quality of another RAG system. It calculates scores for faithfulness, answer relevance, and context precision, providing a quantifiable way to measure progress during development iterations.
Instead of fetching a fixed number of documents, use a distance threshold. This dynamic approach only returns documents that meet a specific similarity score, preventing the model from receiving low-quality or irrelevant context when no good matches exist in the database. Prompt compression removes redundant tokens from retrieved documents before passing them to the LLM. This saves costs and improves processing speed, while ensuring the core semantic meaning remains intact for the generation task. Combining vector databases with knowledge graphs allows the system to traverse explicit relationships between entities while maintaining the benefits of semantic search. This hybrid structure is the current state of the art for complex reasoning in RAG architectures. Vector drift occurs when the distribution of user queries changes over time or the underlying embedding model is updated. Continuous monitoring ensures your search indices remain aligned with the current language patterns and document formats of your application. Avoid blocking the main application thread during document ingestion. Use asynchronous pipelines and message queues to handle embedding and indexing. This architecture ensures the user interface remains responsive, even during heavy data synchronization tasks. Vector storage costs are driven by dimension count and index type. Reducing vector dimensions via PCA or using simpler indexing algorithms can significantly lower your infrastructure bills without drastically impacting the final quality of the retrieval system. Security must be handled during retrieval. By injecting user permissions directly into the metadata filters, you can ensure that the vector database never returns information that the current user is not authorized to see, preventing data leaks in enterprise RAG systems. As vector databases evolve, they are becoming active agents that decide when and how to search. Mastering these architectures is the key to building resilient, scalable, and intelligent applications that leverage the full power of modern large language models.